New York. She's going to talk about comparing phylogenetic trees.
Hi. So this is going to be a very mathematical talk. This is a joint work with Maria Luisa Bonet at Catalunya Polytechnic University. So what I'd like to look at is, when are two trees similar? These two trees are based on a mitochondrial DNA analysis. And if you look at them, it's pretty difficult to figure out which one is which. And I'd like to say there's been many ways to figure out how two trees are similar. One, for example, is to just measure the number of branches that differ. And we've heard about that several times already, false positives plus false negatives. Another way is to give credit for when you get subtrees or details right. Another one is to give credit for overall structure. So the first one, which is probably the one that you'll see most common in simulation studies, is the Robinson-Fools distance, which is just asking when, how many branches occur in exactly one tree. Why do you see this a lot? It can be calculated in order and time, so it's linear, and it works really well with weighted trees also. Another distance, which is more interesting, at least I think it's more interesting, is the tree bisection and reconnection distance, which is if you start with this tree and you break any given edge, and then reconnect two other edges to form the tree on the far right. We'll call that a single TBR move. And the TBR distance is the minimal number of TBR moves to transform one to the other. So this was shown to be NP hard by Mike Steele and Benjamin Allen. And there's been many attempts to show an approximation algorithm for this with guaranteed bounds, several in press. There currently are none. Another related distance, and this is the one I'd like to talk about today, is subtree prune and regraft, or SPR. For this one, you take off a subtree, but keep it rooted, and graft it somewhere else in the tree. And similarly, we'll say that the SPR distance between two trees is the minimal number of moves to transform the first into the second. So this one was shown to be NP-hard by Magnus Borderwich and Charles Semple. And there's an approximation algorithm for it on rooted trees that's a linear time approximation, but unfortunately only gets within a multiplicative factor of 5, so it's not very good. But let me actually talk about some interesting problems. So Paul Erdős was famous for giving numerous prizes for his favorite problems in combinatorics, graph theory, and number theory. And this is a picture I borrowed from Mike's webpage. The caption was "Walking in the Park." I think hunting for buttercups also, I'm not sure. So following that tradition, Mike Steele has offered a number of prizes for his favorite problems. And this is my favorite problem of Mike's, which is if you're given two trees, let's stick with unrooted right now, and you shrink their common subchains. So the two trees on the left have subchains of length n, and you shrink those to chains of size 3, does it preserve the SPR distance? If it does, it implies fixed parameter tractability. So Allen and Steele showed this was true for TBR, that shrinking the common subtrains preserves TBR distance. Borderwich and Semple showed it for rooted trees and asked for the reward and were told no. And so what about unrooted trees? And so I should say we haven't solved the problem, but we've made some progress. That's the punchline. So let me say some of the things that are already known about it. Glenn Hickey and a group of about 5 other people showed that it's NP-hard, and that they showed also that the distance of the reduced trees is at most 2 smaller than the original trees, which is actually very nice to have. So this was in a preprint from 2 years ago. And what we can do is actually improve it to being 1 less. So if you reduce all these trees, if you reduce all the chains, every time you reduce a chain, you can lower the distance by 1. At least that's what our bound shows. We don't believe it. We believe Mike's right. But let me talk about this. From our result and a couple of other observations, we can actually show that rooted SPR is fixed parameter tractable. And what do I mean by fixed parameter tractable? that means that you can separate the hard computation with respect to a parameter k. Our parameter k is going to be the distance. So we can decide in a polynomial in n times a really terrible function in k that two trees are distance k. Okay, so our polynomial in n happens to be linear, and our f of k happens to be super exponential. But we can't actually do it, okay? Not so great that way, okay? This relies basically on two nice facts. One, that the subchains, when you reduce these chains, that they are bounded. It doesn't lower the distance by more than either 1 or 2. In this reduction, our proof will work with either 1 or 2. And that for all trees, if you have more chain elements than you have number of moves, it doesn't change the number of moves. So we can shrink all of the trees, and then we don't have to grow them up too high to check for the fixed parameter tractability. So let me just say, I'm running out of time really quickly. So let me just say the idea for improving the lower bounds. We were inspired by Glenn Hickey and that group. Their idea was to treat common chains as subtrees, and that's how they got the -2. We just went very carefully step by step and noticed that you can get the -1 bound. I can give more details afterwards if people are interested. For the fixed parameter tractability, what we did was very similar to what Mike Steele and Benjamin Allen and Charles and Magnus did, which is first thing you do is you reduce the trees by the subchain rule. And you should, one of the things that Mike showed was that if the distance is less than k, the reduced trees are less than 28k. So the trees are bounded by k. And then you go brute force and check every set of moves that transforms the first tree to the second and see if it works. So that's the standard way to do it. Now, that would be great if we actually had that SPR distance was preserved under the chain reduction. We don't. So what we have to do next is for every possible set of moves, check the transformation. And what do I mean by checking the transformation? We have to extend the chains back out and try them. Okay, this is where we get the super exponential. We end up with a huge number of things to check, but it only depends on k. It doesn't depend on n. So we end up with the fixed parameter tractability. And that's actually what this says, is dividing the steps by which depends on k and which depends on n. Okay, so what does this leave? This still leaves Mike's favorite problem. The prize is $100 New Zealand or American?
Whatever.
Okay. Or, from what I understand, accommodation. Okay. And this is.
Same these days.
What? Excuse me?
Almost the same these days.
Pounds?
New Zealand is not.
Oh, okay. I like the pounds better. That's. So yeah. So this still leaves this question: if you take two trees with common chains and you shrink them, do you get the same distance under SPR? And no one knows, so it'd be a great thing. From what I understand, you can also, instead of taking the $100 pound, you can get free accommodations, right, at the next phylogenetics meeting in New Zealand. Not airfare, right? Okay. So I'm going to stop there and just say I want to thank the Newton Institute and the National Science Foundation. Sorry, I went super fast.
Okay, you have time for lots of
Sorry.
Yes.
Are there distances based on largest common subgraphs, connected or disconnected?
I'm afraid I didn't hear what you said.
Are there distances between trees
Mm-hmm.
based on largest common subgraphs of those trees, whether they are connected or disconnected? So the idea
Trees are always connected. Right?
Yeah, trees are
Okay.
connected, but we're looking for subgraphs of trees.
Uh-huh.
And
Yes.
so you remove them and you count the number of edges that change.
Right. So the proof for TBR and for rooted SPR both depend on making a maximum agreement forest, and then everything goes through quite elegantly if you can have a maximum agreement forest. For for unrooted SPR, Nobody knows how to make a maximum agreement forest. And there's been many, many attempts, and it just hasn't worked. And it has something, it's kind of an odd thing because you're dealing with unrooted trees, but you're dealing with a rooted move. Yeah, so if you can figure that out, then you can talk to Mike.
Okay. Then we should move on to the next speaker. I'll announce when he's got the microphone on.